Okay, so let's continue. Last week I have given you a brief introduction about fluid mechanics too. Unfortunately, due to the time constraint, you won't have a Kahoot last week. Right? You did not have Kahoot last week. Usually I have it, but this time, 12th week, man, we cannot do that. Time is not our leisure anymore. Okay, so I think you know most of the topic that will be covered in this classroom, right? If you have any question, please raise your hand and ask. If you're afraid, right? Some of you, your pride is very high. You do not want to look like you ask something in the classroom. You may approach me after the class or in my room, right? The room is there. So I will try to answer if I can. If I cannot, we try to search for it together. Professor Google is there. He can give you fatwa, he can give you anything, right? You can be a judge just by looking at Google. That's what they do now, right? Of course, it is not right. So this is the question from one of my students last 3 years ago. You know, he's here, I remember he's sitting there on that side. He's taking fluid mechanics 2, right? Fluid mechanics 2, not fluid mechanics 1. Not in the first year, not in the fundamental. This is in the 4th semester. He raised his hand, he asked me, "Sir, why do we need to learn fluid mechanics?" Any one of you want to ask that now? Why do you learn fluid mechanics? Right? The ultimate answer is because you are a mechanical engineering student. And somehow, on that syllabus of your mechanical, you need to take this. But that is, of course, a very bad answer. The right answer is because we need it in our daily life. You know that fluid mechanics is everywhere in your life. Okay? Even if you want to kill yourself, you puncture your heart with a knife, you will still see fluid flow. Right? Which means you still have a fluid mechanics out of it. Because you hate fluid mechanics so much, you do that, suddenly you see, oh, this is still fluid mechanics. I cannot run away from it, right? When you were buried there, your body fluid will start to flow out of your body. So still fluid mechanics is there, unfortunately. Right? If you believe in heaven and hell, you know, in heaven they'll still have a river. Right? Greenery with a river within it. So unfortunately, even like that, you still have a fluid mechanics, right? So fluid mechanics is everywhere in your daily life, right? When you drive a car, fluid mechanics is there. Inside your engine, there is a fluid moving. Your piston is moving, compressing the fluid, right? Outside your car, air is coming to you, right? That's also fluid mechanics. Within your body, right? Your heart pump the blood, fluid mechanics. You drink a coffee, fluid mechanics. Who had fluid mechanics that you do not want to be involved with fluid mechanics? You can forget about it. Even you die, you still have fluid mechanics with you. Okay? Hope that's sending a strong message to you about the importance of it. Okay, especially for our boys and girls who love a car, fluid mechanics is very important. Okay? You will later on know that if you have a sedan that is not four-wheel drive, okay, which is not four-wheel drive, and you try to install a spoiler, you will not enhance the performance, but you really spoil the performance. That's why it's called spoiler. Okay, we will learn about it later. Okay, so we will let you know later about it. Of course, when you design an aircraft, it's very important Okay, when you design aircraft nowadays, you do not design like, okay, I want to build aircraft, I just build it. No, you need to do testing, and most of the testing now is not conducted in a wind tunnel test, but using a CFD, computational fluid dynamics, because it saves a lot of cost. Right? Okay? And if you are gamers, now you know in a gaming computer, the number of fans is increasing tremendously. 1, 2, 3, 4, 5. Not enough fan, you put liquid nitrogen to overclock it. How many of you do overclock? Right? We have new Intel 9000 series. Overclocking. Or maybe AMD Ryzen. Okay? So, if you want to overclock, you need to have a good understanding on fluid mechanics also. Okay? So in all of this application, understanding of fluid mechanics is utmost important. Now the problem is, how do you predict the fluid mechanics or the fluid movement? I think I have told you, right? Last time, what happened if you have a car, right? If you have a car, okay. You know Mr. Machine, right? Scooby-Doo. Right, the velocity is 30 meters per second. Then who is that? Shaggy. Push the pedal, and the acceleration is, let's say, 3 meters per second square. Within 10 seconds, right? You can predict what is the Vt and what is the S. That is for this car. Now what happens if you have a flow? If you have a fluid, I do this. Now the air in this, let's say this one is my air. Now I play the role as a fan. I do that. Of course the air will move. Now how do you predict the movement? Okay, so in this classroom, we will learn how to drive Navier Stokes from the scratch. Have you ever heard this? This is called Reynolds transfer theorem, RTT. You got it in your fluid mechanics. One before conservation of mass, before the finite volume analysis. Okay? So basically, if you are dealing with that car, you are dealing with control car. You are dealing with control car. Good. Control finance. Control system. It's even worse. I told you. Control mass. Right? When you are dealing with the car, you are dealing with the control mass, which means the mass is constant. Right? The mass is constant. When you are dealing with the control mass, you follow the movement of this mass. When it flows, look at that. Right? The velocity, the acceleration, and the distance of that thing from the original point. Now the problem when you are having a fluid, you cannot do that because fluid is continuous material. Right? That's why you are dealing with control volume. So when you are dealing with control volume, you take a constant volume. Right? This is my constant volume bounded by this. So what I want to see is what is coming in, what is coming out, and whatever retained within the control volume. The problem is all our governing equation is derived based on physics law, which is mostly on control mass. So to relate control mass and control volume, we are using this RTT, Reynolds transfer theorem. I hope you already understand about it. So now if you have control mass, this is your control mass, right? This is the mass. You convert it from control mass to control volume. Any question about it?
No.
No? Good. Because we will use it all the way. Okay? So, if we are taking a small cubical control volume and you do that Reynolds transfer theorem, I will not go into detail because I don't want the whole class to form it because of this. Right? If you have any question or if you want to derive on your own or if you want to ask me how to derive it, you can leave me a letter, right? How to derive it. Basically, you take a very small volume of air. Let's say this one is your air, right? You take a small cube on this air, kind of our imaginary cube, right? You take imaginary cube. In those imaginary cube, you take the rho, which is the density. So rho times volume will give you mass, right? You know why why we are doing m is equal to rho dV is because if you have this, the density here can be different with density there, can be different with density there. This is the reality of our life. Right? In your physics, you take it as a lump sum. Even though you are talking about car, you take it only the mass of the car is 5 tons. That's it. But in reality, the front part of the car, the density is different with the rear part, bottom part, and top part. That's why when we are talking about fluids, this comes from, yeah. Okay? So hopefully no confusion about that, why we have all of those things. Okay, don't worry. Okay, so if you take that and you take a Taylor series, okay, this Taylor series is not the one that's singing, you are my prince, no, not Taylor Swift. This one is Taylor series. Not Taylor Swift. This Taylor series says that if you want to have the function, you can take the value in some point, right? And then they take the derivation, first derivation with permeation continuously, and then you will end up having this for that equation.